New observations from the Gemini North Telescope in Hawaii have provided astronomers with compelling new insights into the interstellar comet known as 3I/Atlas, confirming that the object has grown noticeably brighter and developed a distinct greenish glow following its close flyby of the Sun in October. This transformation marks a significant increase in the comet's activity and suggests that it is undergoing rapid physical and chemical changes as it continues its journey through the inner solar system. Captured on November 26 from the summit of Mauna Kea, the Gemini North images show 3I/Atlas in one of its most energetic states observed so far, offering scientists a rare opportunity to study how an interstellar visitor responds to intense solar heating. As 3I/Atlas passed close to the Sun, it was subjected to powerful solar radiation that dramatically warmed its surface. This heating caused volatile ices embedded within the comet's nucleus to sublimate, transitioning directly from solid to gas. As these gases escaped into space, they carried with them significant quantities of dust, creating a rapidly expanding cloud of material surrounding the comet's core. This cloud, known as the coma, has grown brighter and more pronounced, while a long, luminous tail now stretches behind the comet, shaped by the pressure of sunlight and the solar wind. Such behavior is typical of comets originating within our own solar system, but observing it in an interstellar object provides valuable clues about the composition and structure of material formed around other stars. To analyze the changes in 3I/Atlas in detail, the observing team used 4 different filters: blue, red, orange, and green, allowing them to separate and study various components of the light emitted or reflected by the comet. This multi-filter approach revealed that gases within the coma are now emitting a faint greenish light, a feature that was not present in observations made several months earlier. This green glow is not evidence of anything extraordinary or artificial, but rather a well-known phenomenon in cometary science. Among the gases released by the comet is diatomic carbon, or C2, a molecule composed of 2 carbon atoms. When energized by sunlight, this molecule emits light in the green portion of a spectrum, giving many active comets their characteristic emerald hue. The presence of diatomic carbon in the coma of 3I/Atlas aligns it with numerous comets native to the solar system, which often display a similar coloration when they become active near the Sun. Recent examples include Comet 12P/Ponsbrook's, sometimes nicknamed the Mother of Dragons, as well as the more recently discovered Comet C/2025 F2 Swan. The fact that an interstellar comet exhibits comparable behavior suggests that some of the basic building blocks and processes involved in comet formation may be common throughout the galaxy. This supports the idea that the materials from which planetary systems form may share fundamental similarities, even when they originate around entirely different stars. What makes 3I/Atlas particularly intriguing, however, is how dramatically its appearance has changed over time. When the comet was first observed by the Gemini South Telescope in Chile in late August, well before its close encounter with the Sun, it appeared distinctly redder. That reddish coloration likely resulted from sunlight reflecting off dust-rich material on or near the comet's surface, with relatively little contribution from gas emissions. The shift from a red-dominated appearance to one featuring a noticeable green glow indicates that the comet is now releasing new molecular species as it heats up. This transition provides strong evidence that the interior of 3I/Atlas contains volatile compounds that were previously trapped beneath its surface and are only now being exposed. Such changes offer astronomers a rare window into the internal makeup of an interstellar object. Unlike comets that have orbited the Sun many times and may have lost much of their original volatile material, 3I/Atlas is likely making its first and only pass through our solar system. This means its composition may be relatively pristine, preserving information about the environment in which it formed. By studying the gases and dust it releases, scientists can infer the chemical conditions present in its home star system billions of years ago, gaining insights that would otherwise be impossible to obtain. The increasing activity of 3I/Atlas also raises the possibility of further dramatic changes in the coming weeks. As the comet continues to adjust to its new thermal environment, additional outbursts of gas and dust may occur. These sudden releases could temporarily increase the comet's brightness or alter the structure of its coma and tail. While the comet is not expected to pose any danger to Earth, its dynamic behavior makes it an exciting target for both professional astronomers and advanced amateur observers. On December 19th, 3I/Atlas will reach its closest point to Earth, passing at a distance of approximately 170 million miles, or about 270 million kilometers. This is a comfortable and safe distance, but close enough on cosmic scales to allow for detailed observations using ground-based telescopes and potentially space-based instruments as well. During this period, astronomers will be watching closely for any unexpected developments, such as changes in brightness, new jets of material, or shifts in its spectral signature. Each new observation adds another piece to the puzzle of understanding this rare visitor. The study of interstellar comets, like 3I/Atlas, represents a rapidly developing frontier in astronomy. Until recently, such objects were purely theoretical, with scientists speculating that comets and asteroids ejected from other star systems must occasionally pass through our own. The discovery of the first known interstellar object, 1I/Oumuamua, in 2017, followed by the interstellar comet 2I/Borisov in 2019, confirmed these predictions and sparked intense interest in the field. 3I/Atlas now joins this small but growing group, each object offering a unique perspective on the diversity of materials beyond our solar system. Unlike Oumuamua, which showed ambiguous signs of cometary activity, 3I/Atlas is clearly behaving like a classic comet, complete with a coma and tail driven by sublimating ices. This makes it particularly valuable for comparative studies, allowing scientists to directly compare its behavior with that of well-studied solar system comets. By examining similarities and differences, researchers can test theories about how common certain chemical compounds are in planetary systems and how comets evolve under stellar radiation. The greenish glow now observed in 3I/Atlas is therefore more than just a visual curiosity. It is a signal that complex carbon-bearing molecules are present and actively participating in the comet's interaction with sunlight. Carbon is a key element in chemistry and, ultimately, in the processes that lead to life. While there is no suggestion that this comet harbors life itself, its composition contributes to a broader understanding of how carbon-rich materials are distributed throughout the galaxy. As observations continue, 3I/Atlas may yet reveal additional surprises. Its activity level could increase further, or it might stabilize as it moves away from the Sun after its closest approach to Earth. Either way, the data collected during this brief window will be studied for years to come, helping astronomers refine models of cometary physics and interstellar object dynamics. Each spectrum analyzed and each image captured adds depth to our understanding of how objects from distant star systems behave when they encounter a new stellar environment. In the end, the brightening and greening of 3I/Atlas serve as a vivid reminder that our solar system is not isolated, but rather part of a dynamic and interconnected galaxy. Objects formed around other stars can and do wander into our cosmic neighborhood, carrying with them stories written in ice, dust, and gas. Through powerful instruments like the Gemini North Telescope and the collaborative efforts of international scientific institutions, humanity is now able to read those stories, transforming fleeting points of light in the sky into profound sources of knowledge about the universe beyond our own sun.